In this video, I want to discuss the concept that the F statistic is the square of the T statistic. Tuesday's class, I said that the T value that you see here, if you square that, you'll get the uh, mean square, I'm sorry, you'll get the F value. Okay? And of course, here we don't do a test for t for the intercept. We don't do a test for categorical variables because there are multiple dummy variables that constitute one categorical variable. So that left us with just these two. And when you square this t, well, it's not this f. Okay. For kilometers, it is, but for weight, it is not. So, um, well, somebody pointed that out to me. I'm glad that people are paying attention to me in class. So that's a great thing. Um, so, so how come I said the square of t is f and it is not, and what's the explanation? And I said in class that I'm going to dig into this and get you an explanation. And I promised you that what I said is true. T squared is equal to f. And so here is the lowdown. Now, there are three different ways in which the total sum of squares represents the total variation in the target variable. And so part of it is going to be unexplainable, and that was our residual. And the part that is explained by the model, okay, and we have several variables going into the model, and how much of the total sum of squares explained by the model, so that in our case is sum of squares of regression. So how much of it is attributable to each of these three variables? Okay, and there are three different ways in which it can be allocated. One is the sequential allocation. So that is, you bring in the first variable and then see how much sum of squares, the error sum of squares is reduced, and that's attributed to the first variable. Then you bring in the second one, then see how much that reduces the error sum of squares, and then you bring in the third one. So that's sequential. Sequentially, one after the other, you see how much sum of squares is attributable to that variable, and that is called type 1 sum of squares. Okay? And the problem with type 1 sum of squares is that if you change the sequence, the sum of squares attributed to those variables will be different. So instead of bringing in fuel type first, you bring in weight first. Then the sum of squares attributed to the weight is going to be different. So let me explain that to you with a picture. So now if you bring in fuel type first, then you see the sum of squares is this. Okay. And then of course there are two dummy variables associated with fuel type, so you have to divide this by 2 and you get the mean square, and then your mean square divided by the MSE. And again, there is a problem with that MSE too, because we need to use the MSE of the full model, not the MSE when just one variable is in the model. So when you divide that, you get your F. Okay, so that's good. Then you bring in the next variable weight, and that accounts for that much of sum of squares. So the two together is going to be that much. Okay. Now, what if we bring in weight first and then bring in fuel type? So, well, this is the F in that case when weight comes in second, right? So that's when we got an F value which is 797, which was not the square of the T that we saw. So that's because weight came in after fuel, and this was the computation. So now if we reverse this, we bring in weight first, and you can run this in R, and you will see that the sum of squares attributable to weight is different. Okay. Now the mean square is 575. It's not 797. It's still not equal to t squared. Now after bringing in weight and then you bring in fuel type, and again the sum of squares for fuel type is different, and the corresponding f value is also different. So this is what we call type 1 sum of squares, and this is the problem with that. And there are some advantages to this, but there is another kind of way in which sum of squares can be attributed, and that's called type 3 sum of squares. And then there is type 2, and we won't get into type 2. Let's look at how type 3 sum of squares is allocated. So we start with, and this is also called additional sum of squares. Okay. So now we're going to start with the entire model. Okay. So we put in all the variables that we are considering into the model. All three variables are in. So now we have the total sum of squares of regression. So all three variables is this much, and then the mean square error is this for the model. Okay. So now what we're going to do is to take out one variable. Okay. So now leave out the one variable at a time. So now if we leave out weight, so now the two variables that are left are fuel and kilometer, and you run the model, run the LM method with this. Okay, so now we get sum of squares of regression has gone down, obviously, because you've taken out weight. So this difference is what is attributable to weight. So this is called the additional sum of squares. So sum of squares for weight is this. Okay, so difference between these two, and this constitutes one variable. So mean square is that divided by 1, which is that itself, and then we find the f value by dividing the mean square for weight by the MSC, and we get 388.72. Okay. And this is based on type 3 sum of squares. And now, voila, we take the t for weight that we saw before and square that, and it is equal to f. So it is the f computed based on type 3 sum of squares that I was talking about in class. And the reason why I was talking about that is the legacy software like SAS and SPSS and Minitab and all the rest of it, it's always type 3 sum of squares that is computed and given to us as results. And I didn't realize that in R, type 1 is what is displayed and not type 3. So if you want type 3, then there is another library for that called CAR, C-A-R, and we have to use that to get type 3 sum of squares. By default, we get only type 1, and if we want type 3, then we have to do this one at a time. So you first run the entire model, and then in turn leave one variable out and see how much is the difference in sum of squares, and then build that one variable at a time, and you will have the additional sum of squares, and you get your f based on that, and oftentimes that f is called the partial f, and that partial f will always be equal to the square of the t statistic value. And I hope this makes sense. If you have any questions, of course, please let me know.